everybody to our summer school. So we are very excited and happy to have all the students here, all the visiting professors, and especially our guest speakers. So before I introduce our first speaker, I wanted just to mention very shortly, please try to use your badge at all times. And this has the purpose of us knowing each other and being able to talk with each other, but also it's going to make a little bit easier the entrance, okay? So if they see you with the badge, they won't ask your name. So try to speak. Okay, so our first speaker is Sebastian Budek. So we are really, really happy to have Sebastian here. So Sebastian, he did his PhD in France, in Lille. Then he did a postdoc in Faura. Please correct me if I may.
Yeah, so far so good.
He spent some time at the Simons Institute. Then he was an assistant professor at Princeton. And now he's a senior researcher in Microsoft Research. So Sebastian has done some really groundbreaking and fundamental work in convex optimization, in online learning, and statistics in random graphs. And we're really, really excited about the talk he's going to talk us today.
Thanks, Jose. Thanks a lot for this very nice introduction. So I'm really happy to be here. It's my first time in Chile. So far, I'm having a really good time. So I'm going to tell you about Online Lipschitz selection. So it's a slightly different title from what I gave. It's also a non-standard, set like combination of words. So we will see how this goes. Okay, so I'm going to tell you what the problem is and a little bit about the plan for the lecture. And I know it's not easy to ask questions in this setting, but it would be really, really helpful if you could ask questions. If I'm going too fast, which might happen at some point, you really need to slow me down, okay? So I count on you. All right, so I will, so what's going to happen? So we'll have X, which is a finite metric space. So X, or not even finite, it's just a metric space. So it's equipped with a distance. And this will be the background for everything that we talk about. So this will be, you can think, if you prefer, that this is a graph, and you have the shortest path metric on the graph. And another object that will be very important to us is calligraphic K, which is going to be a family of sets. So this is a family of sets in X. Okay, so two typical examples that we're going to look at are just when you have all the subset of X, when X is a finite metric space. Another example that we will briefly look at is a case where X is, say, RD, d-dimensional Euclidean space, and calligraphic K is a set of convex sets. Okay, so we'll talk again about this. So these are the two basic objects. So now what is online selection? So online selection is the following problem. By the way, if you want, you can think of elements of X as a state. So X is a state space, and we're going to think about moving in this state space. So online selection goes like this. So at every time step t, discrete time step, a feasible set is going to be revealed. A feasible set kt, which is an element in our family, is revealed. I will also refer to this set as a request. Okay, this is a request. And what you have to do as a player, as a decision maker in this online problem, is that you have to choose an element in that set. You have to select an element. Okay? So select an element, rho t in kt. Okay, so that's the selection part. You get a feasible set of state, and you have to choose one element. And the cost that you're going to pay is the cost of updating your state. So before you were at some other state, rho t minus 1, and now you're at a new state, rho t, and what you pay is the distance that you have traveled. Okay, so the cost is going to be the distance between rho t minus 1 and rho t. Okay, and what you want to do is to minimize just the total cost. Okay, does that make sense? So this is very abstract, and in fact, it's extremely general, and it covers many online problems in online algorithms, in online learning. It really covers many things, and we're going to talk about some of the specific examples. And for this first lecture, I'm going to talk about some of the reductions from other problems to this formulation. Okay. Yes.
If you want to try on the salesman problem, it doesn't work, right? So if I give you all the sets every time.
Yes. So you want so what do you want to give me exactly?
Okay, so I give you first time I give you a set of all elements.
Yes.
Of all cities.
Uh-huh.
Then you pick up one. Next time I give you the set of all except this one.
Yes. Very good. So one thing I should say, so we're going to talk about whether this sequence is adaptive or not. Okay, so this is going to be something important. So, but there will be a setting in which this sequence can be adaptive, and then you can do that. Yes. Yeah, then that would be reasonable. One thing also that I would point out right from the start is that we're not going to focus on computational complexity. Everything is going to be more about information. You know, it's going to be a course about information theoretic aspect of this question, not really computational aspect. But we're going to go back to this. Okay, good. So now the three canonical cases that we're going to look at, so the three canonical cases are going to be one, the finite case. So the finite case is when X is of size n, and the family of set is just the power set. Okay, so it's all the subsets. So this we're going to spend one lecture on this. So one lecture on this tomorrow. Then, and I will explain how it relates to a famous problem which is called the metrical task systems. Okay, so this I'm going to explain today how this reduction works. Another important case is a convex case. So in the convex case, X is again d-dimensional Euclidean space, and K is a set of convex sets in RD. Okay, so I won't dedicate a lecture to this one. It's a very interesting case, but we won't have time to cover it. It's also less combinatorial than the other ones. But today I will make a few comments about this one. Okay, this is also the one that has the most history in some sense, going back to the 19th century. Okay, and 3 is going to be the K-server problem. And on this, I'm going to spend 2 lectures. So this is really the main event, is to give you the state of the art on K-server. So what is K-server in this formulation? K-server is, so there are several ways to put it in this framework, but the one that I like, which is nice to think about, is like this. So kappa is trivial, by which I mean it's all singletons. Okay, so the requests are just singletons, just a single element in your metric space. You have to choose that. Okay, so then in that scenario, it doesn't make sense. You know, you just go there and that's it. There's nothing to be done. The twist is that instead of maintaining a single state, we're going to maintain k-states. But one maintains k-states. Okay, so instead of having a single agent moving in the metric space, I'm going to have a fleet of k agents moving. That's what I'm controlling. This is a K-server problem, and what we're going to do for this finite case is going to be very useful for the K-server problem. Okay. Good. So today, so this first lecture, so this chapter 1, for this first lecture is just an introduction. And in this introduction, I'm going to tell you about some reduction and then give you some feel for this question and also what we're trying to achieve exactly, because I didn't explain yet what is the goal exactly, how do you evaluate if a strategy is good. So that's what I'm going to talk about. This afternoon, we're going to talk about gradient descent. So how does gradient descent, you know, how can you do gradient descent for a problem like this? It's not obvious a priori. So this is what I'm going to do this afternoon, and then we will move on to finite case and then case server. Okay? So that's the plan. All right. So let's start for the introduction with just the classical selection problem. Classical selection. Okay, so what is classical selection? So classical selection goes like this. A map S which goes from K to X such that S of K is in K. Okay, so for any set in my family, this map S on that set outputs an element of K. This is called a selector. It's called a selector. Okay, so it just selects in my family of set. For any set, it selects an element. That's called a selector. So this has a very long history, you know. A little bit more than a century ago, mathematicians were fighting about the axiom of choice, which is just whether a selector exists. Okay, so in a very general setting. A little bit later, there was okay, maybe before I go into the history, what do we want about this selector? Yeah?
That K is the same as the family of sets?
Yes. Let's say, so this, you know, X and K, these are just background, and they are going to stay with us for the rest of everything.
Yeah, but I don't understand how a set, because S is defined to X.
Yes?
And a set.
Yes. So this is a family of sets, and these are the elements in those sets. So what this map does is that it takes a set, and it outputs an element in that set. So this is a set, this is an element, and that element has to be in that set. That's what I mean by that. Thanks a lot for the question. Okay. Good. So let's say we don't worry about the existence, you know, we accept the axiom of choice or things like that, which is we're not going to have to worry about this, okay? Don't worry. But let's say we have such a selector. Then the next question becomes, can you find a nice selector? Okay, so the big question is, does there exist a nice selector? And what we mean by nice is going to depend on the structures that you have on X. Okay? But here the structures that we have on X is a metric structure. Okay? So when you have a metric structure, the natural question to ask is smoothness, regularity. Okay? Or to put it differently, Lipschitzness. Okay? This is the natural question to ask when you have a metric structure. So here we have metric structure. So the natural question, so nice means Lipschitz. Okay, and again, Lipschitz, you know, it just means, right, a map is Lipschitz if when I change, I move a little bit the input, the output also moves a little bit. Now, what is the input of such a map? The input is a set. So what does it mean to move a little bit a set? I need a distance between set. Well, there is one very natural distance, which is the Hausdorff distance. Okay, so let me just remind you, so the Hausdorff distance is defined like this. So between two sets, let's say K and K prime, it's the following quantity. So the Hausdorff distance is just from the worst starting point in K, how far do I have to travel to get into K prime? Okay, so it's a maximum over rho in K of the minimum over rho prime in K prime of the distance between rho and rho prime. Okay, again, the interpretation is from the worst starting point in K, how much do I have to travel to get into K prime? And this has to be symmetric, so in fact it's the maximum between that quantity and the same quantity when K and K prime are flipped. Okay, so it's the maximum between this and max over rho prime in K prime, minimum over rho in K of the distance between rho and rho prime. Okay, another way to put it, the Hausdorff distance, is how much do I need to inflate my set so that they contain each other? Okay, that's.
It's obvious that this is the distance.
Well, it's. Is it obvious that it's a distance? Maybe not obvious, but if you write it down, you will see it. Yeah. Yeah, you just use the property that this is a distance. I mean, maybe the nicest way to see it is this picture that it's the smallest epsilon such that you have to inflate the set. Okay, so you have those two sets, and you're asking how much do I need to inflate so that I contain the other set. And when you write it like this, then you can see the triangle inequality. Okay, good. Okay, so this is the notion of stability between two sets. And now we will say that the selector is Lipschitz, is let's say L Lipschitz, if for any K and K prime in my family of sets, I have the distance between S of K and S of K prime, which is smaller than L times the Hausdorff distance between K and K prime. Okay, so this is what it means to be Lipschitz. Okay, so again, it means that if I have two sets which are not too different from each other, the Hausdorff distance is pretty small, then the points which are selected are also not too far from each other. Okay, it's a stability property, or a robustness property, if you wish. Okay. So this question has a distinguished history in the convex case, and we're going to briefly talk about it. This is basically the only thing, essentially the only thing that I'm going to say about the convex case. So here is a theorem.
Sorry.
Yeah.
So some simple example about Hausdorff distance.
Yes, I'm. Let me think if I want to do that. I'm gonna do the following. So, I mean, just imagine if you have, a set like this, and this set. Okay, so the Hausdorff distance is just this distance. Does that make sense? It's just, you have this initial set, so let's say when they are contained in each other, it's very simple. Yeah, maybe let's say if K prime is contained in K, then the Hausdorff distance is just how much do I need to inflate so that K prime plus epsilon times a little bit, times a ball, this contains the other set. Okay, the thing which is a little bit tricky to think about with the Hausdorff distance is when the two sets are not contained in each other. Then it's a little bit more complicated. But anyway, we're gonna very soon. So the main part of the course is about online, and in the online case, we'll have a very natural interpretation of Hausdorff, where in particular we will drop this max, and there will be an order between K and K prime, so it will be easier to think about. Okay. Good. So the theorem that I want to tell you is the following. In the convex case, there exists O of square root d Lipschitz selector. And this is the best one can do. And this is the best one can do. Okay, so again we're in dimension d. And this theorem is saying that there exists a selector which is Lipschitz up to a Lipschitz constant square root d, and you cannot get a constant, Lipschitz constant which is better than square root d. Okay, so this is a folklore result. So this is, let's say, folklore. For the upper bound, there is a paper by Vitale from 85. And the lower bound, it has a really long history. The lower bound that I'm not going to explain now. You can ask me offline if you're interested in this. But the point is, okay, so we're going to prove a slightly weaker version of this, and I want to give you a feel for what is a selector and how does it work. Yeah, it's constructive, and I'm going to tell you what is actually the optimal selector for convex sets. Okay, we know exactly this answer. It's really beautiful. Okay, so I'm not calling it proof, but more like comments because we're not exactly going to prove this. So maybe maybe let me ask this: what if you had to propose a selector for convex sets? Do you have any proposal? So again, a selector is just I take a convex set and I output some point in the set. What would be a natural point? The mean, exactly. Yes, exactly, the mean. Okay, so natural, very natural, thank you for suggesting that, is a mean. Also called the center of gravity or centroid. You know, it has many names. Okay, I'm really glad you suggested that. It is indeed the most natural. This is absolutely not Lipschitz. Okay, this is very, very non-Lipschitz. But it is the most natural one to think about. Here is what happens. So think that I have a small triangle like this. A very, very thin triangle like that. Okay? So where is the center of gravity in this? The center of gravity is going to be, 1/3 of this distance here and 1/3 here. So the center of gravity is something like here. Okay, where this is like 1/3 and this is like 1/3. Okay, so this is the center of gravity. But you see, as I collapse this dimension, as I make this go smaller and eventually go to 0, then the center of gravity moves from this 1/3 to 1/2 0. Okay, so when you move to just literally a segment like this, you move to 1/2. So you did, in the space of sets, you did a microscopic move, but the selector did a macroscopic move. Okay, so this is not Lipschitz. All right, and this is not robust, and this is a very well understood problem. So maybe if you were thinking, 5 minutes about this problem, a natural one to come up with is what's called the Chebyshev center. So, okay. Second guess. Yeah?
So more or less I follow the intuition, but what is the worst case that can happen if you select the mean? What is the set that the adversary can give you?
Yeah. So basically, what those two examples show, so a triangle and the corresponding segment, a thin triangle and the corresponding segment, shows that no finite L can work. This is just infinite. Okay, so if you want, the worst case is exactly what I drew here. Give, this is K, and this is K prime. Okay, so K is this very thin triangle, and K prime is just the base. Yeah. So if I do that, then your selector is making a big move. But the sets themselves are changing very, very small because, okay, maybe I didn't, it's obvious, but the Hausdorff distance between this and that is just this epsilon, right? Yeah. Okay, so the second guess is a Chebyshev center, which is the following. It's the point which is the closest to its furthest point. Okay? Point closest to its furthest point. I mean, if you think about it, this makes a lot of sense if you want to have something stable. You want to be deep inside, okay, in some sense. Or another way to put it is, you know, for any point, I can look at how big of a ball I need to contain my set. And the Chebyshev center is a point that minimizes the radius of this ball. Okay, it's really the point which is deepest inside in some ways. And you can see that this is indeed Lipschitz. Okay, such a Chebyshev center. So it is indeed Lipschitz, but it's not the most Lipschitz. Okay, it's not the best. For instance, here, you know, it would, the point of the Chebyshev center is that it's not confused by this collapsing of dimension. It will really recognize that 1/2 is the best here because that's where you have the smallest ball that can contain it. Okay. So actually the best selector, the actually most Lipschitz, and if you think about it, it's such a wonderful mathematical result that you can find the most Lipschitz selector. I mean, this, you can think of it as an optimization problem in very, very high dimension. You're searching over the space of selectors, okay, but we have been able to find the actual best. And the best is what's called the Steiner point. Steiner point. Yeah? Yeah, I'm not sure. I think it's D, but I didn't try to prove it. But I know it has to be Lipschitz. Yeah. Yeah, I think it's D, but okay. If you want, that's an exercise. Okay, so the Steiner point, so this was invented in 1840 by Steiner. I still don't know exactly why he invented it. I know it was some combinatorics problem, some extremal combinatorics, but okay, I'm still trying to find the origin of it. But in any case, here is the definition. So I would say those two were natural. This one, the formulas that I'm going to write, it's highly non-trivial. So the formula is going to be like this. Let me remind you one element of convex geometry, which is a support function. So hk of theta, so K is a convex set, right? Or a convex body, let's say. Hk of theta is going to be, it's a maximum over x in K of the inner product theta dot x. Okay, so it's, I pick a direction, so maybe let's put it like this. So this is K. And let's say I pick a direction theta, then I'm trying to maximize the inner product x dot theta for x in K. I find this point, and I record the value of x dot theta. This is the value of the support function. Okay, so this is a very natural function. And the Steiner point is the expectation when I take theta at random from the sphere. Okay, so I take a random direction. And I integrate theta times hk of theta. Okay, this is the formula for the Steiner point. How am I doing it? Okay. So first question, why is this a selector? Why is this in K?
So are you assuming that K is center?
No, so yeah, so there is a lot of magic going on in here, but one of them is, notice that centering doesn't matter because you see, if it's very off-centered, I mean there is theta and then there is minus theta. So things are going to cancel. There are lots of cancellation going on. I mean, that's often the point, is that when you want something optimal, you need all of those cancellations, and yeah, this is what's happening here. So okay, so a proof, yeah? SD minus 1, yeah, sorry. This is a sphere in dimension D, the Euclidean sphere. Yeah. Yeah, just the Euclidean sphere in dimension D, yeah. All the points which are at Euclidean norm 1. Okay, so the fact that this is a selector, I know two proofs. I mean, there are two proofs, basically. One of them is by looking at this formula and recognizing that a point is in the convex set if when I optimize over any when I look at the value in any direction theta, I get a value which is smaller than the support function. Basically, the support function, you can think that, it's giving me a bunch of hyperplane that define the convex set. And so I can just look at what is the value of the inner product of this, and you see it's always going to be smaller than hk. Okay, so I get this property exactly that I want. So that's like a dual proof. Okay. The one that I prefer, because I don't like this dual proof, when I look at this, I still don't understand what this is. But there is another formula, which is by doing an integration by parts. And then when you do this integration by parts, you get a formula that makes sense. So I will just do the integration by parts. I mean, just write what is the result. And you can believe me, or, if you want as an exercise, you can try to remember what is Stokes' theorem or Gauss divergence. No, these are the same things in this setting. But in any case, when you do the integration by parts, here is what you get. You get that this is equal to the expectation of, in fact, the gradient of hk theta. And here I'm being a bit careless because, maybe you're going to tell me this is not differentiable, etc. I really mean, so this is differentiable, say, for a polytope almost everywhere. Okay, so this is a fine formula. So really, what is the gradient? Maybe the gradient of hk is just the argmax. This is the argmax of theta dot x for x in k. Okay, so again, the definition of gradient of hk is that when I take a direction theta, it actually gives me the extremal vertex. It gives me the maximizer. And now what the Steiner point is doing is that it's taking a random direction, looking at the extremal point, and then just averaging those extremal points. So now you see that this has to be in the set. Okay. And in fact, once you have this formula, there is another name for it that comes up, which is curvature centroid. Okay, so this is also called the curvature centroid. And now we see why. Let me explain. So at any vertex here, I have a normal cone. Okay, so this is going to come up again this afternoon. So this is a normal cone, nk at x, if this is x. Okay, so the normal cone is just a cone which is spanned by the tight constraint at my vertex. I'm going to explain this again this afternoon, but just it's a warm-up. So you have this normal cone, and then you have the dual to the normal cone, which is this thing. So I do 90 degrees here and 90 degrees there. This is a dual. This is a dual cone. And you see any direction theta which falls into this dual cone, when I maximize, I'm going to get at this point. So really, this dual cone, all the dual cones at all the vertices of a polytope, they make a decomposition of the sphere. So what happens is that when I take a direction theta, I can just look at which element in that decomposition I fall in, and that tells me which vertex is going to be the maximizer. So the way to think about the Steiner point is that I have those dual cones, and I can just look at the mass of those dual cones, how big they are, and this is the mass that I assign to each vertex. So I'm just putting to each vertex of my polytope, I'm assigning a mass which depends on the size of the dual cone. Okay, and then I'm integrating and I'm summing those things, and this is a Steiner point. Yeah. Yes. Yes. So when you go to actual convex sets, you will get the Gauss curvature. That's what you're going to get. So formulas are a little bit more complicated because if it was, say, a sphere, you know, all the normal cones are just rays. So you need to understand it's all about the derivative of those things. So we don't want to get into that anyway. It's kind of, it's fun, but you know, all the intuition is in the polytope case. Yeah? Yes, very good. So in this thin triangle, you see what's going to happen. Okay, very good. Look at the dual cone here. The dual cone is this huge thing, you know. It's not of mass a half, but almost. You see, it's just missing a little bit here. Okay, but it's almost a half. And those dual cone, you know, they are basically 1/4. It's basically, you know, here, like this, and here like that. Okay, so this is exactly 1/4 mass. This is going to be like 1/4 plus epsilon, and this is going to be 1/2 minus epsilon. So this is the mass that you assign to each of those vertices. You assign 1/2 minus epsilon here, 1/4 plus epsilon, 1/4. So what you will get is basically you're going to be around 1/2, a little bit off 1/2. So it is very robust. It exactly does the right thing. So let me do the proof that the Steiner point is not square root d Lipschitz, but d Lipschitz, just so you see that it's one line. And then I will give a hint of how you prove square root d. And then we will move on to what this course is really about. Okay. So I'm interested in the distance between sk and sk prime. Right? But I'm in Euclidean space, so the distance is just given by the Euclidean norm. Okay, so it's the norm of this. This is what I'm interested in. So what is this? This is the norm of the expectation over theta of theta times hk of theta minus hk prime of theta. Like this, and the norm. Okay, so this was this magic formula where there are lots of cancellation in it, but this is the one which is useful. Now I can just apply the triangle inequality, or Jensen, or whatever you want to call it. I put the norm inside the expectation. Okay. So now what do I get? I get this is smaller than the expectation over theta of the norm of the same thing. But I know what is the norm of theta. The norm of theta is 1. Theta is on the sphere. Okay, so this is equal to the expectation over theta of just the absolute value. What did I oh, I forgot something. Yeah, sorry, I'm going to explain what I forgot. When you do integration by parts in high dimension, there is a factor that comes out, which is basically how the measure is changing from dimension d to dimension d plus 1. So what I forgot, and I'm sorry about that, is that there is a factor d here. That's very important. Okay, so there is no, here this was the right formula. I mean, this is the only formula that makes sense. But here in this magic formula, I forgot that there is a factor d. Which also again tells you that there are so many cancellations, you basically need to scale things up by a factor d. Okay, so there is a factor d here. Sorry about that. D, D, D. And now I won't do it, but for any theta, this is smaller than the house of distance. I mean, it's kind of obvious. Like, you know, the support function, it is a smooth function of the set. Like, if you change a little bit the set, then the support function is just going to change by the corresponding little bit. Okay? So we get that this is smaller than d times the house of distance between k and k prime. Okay, so this shows that the Steiner point is d Lipschitz, is a d Lipschitz selector. And notice that there was only one inequality, which was this triangle inequality. Okay, so let me give you a hint to prove square root d. So hint to prove square root d. You use that the Euclidean norm of, you know, S, say S minus S prime. This is the max over any direction E in the sphere, in SD minus 1, of the inner product between E and S minus S prime. Right? This is a definition of the norm viewed through the dual. Okay, so the Euclidean norm is just I maximize the linear function over the sphere. And now if I fix a direction E, you see instead of the norm, I have E, the inner product of E with this. But then E with theta, so a fixed direction with a random direction, this is of order square root d, 1 over square root d, with high probability. Okay, so I won't explain this because we won't need it in this course. We're not going to talk about the convex case. We're really going to focus on the finite case. But so I don't need concentration, but this is a very important fact that if you take a fixed direction and then you look at a random direction, the inner product is of order 1 over square root d with very high probability. So this means that for in this integration, most of the theta, actually E dot theta is of order 1 over square root d, which is going to cancel with this d, and that's why you get square root d. The fact that, so this is really an exercise, and that will give you the first part of this statement. The second part is not an exercise. It's a really difficult result, and I won't talk about it. Okay.
Just a step when you go from left to right in the equality.
Yeah.
Third line.
So line, yeah, here.
What was the argument?
Yeah. So I just use, so I get the norm inside, right? So I get the norm of this. So, you know, by the gauge property, you know, this is a scalar and this is a vector. So the norm of, you know, lambda theta, this is absolute value of lambda times the norm of theta. Right? So I get the absolute value of this. And then the norm of theta is 1 because theta is on the sphere. So I get this. Yeah? All right. Okay, any more question on this? So this was to give you a little bit of a feel of what is a selector, how you prove classically Lipschitzness. Now we're going to talk about the online setting. And I realize that I'm going slower than I was thinking, but that's okay. No, yeah, this is for any sets. Yeah, this is very nice. This is really strong. Yes, when I say constructive, I mean there is a formula. It's not. I don't mean there is an efficient algorithm. Yeah. Yes, this is. Okay, so now we're going to move to online Lipschitz, or online selectors. So I don't remember, it's probably like 2 or 3. Let me see. Yeah. So online Lipschitz. Okay, so now we're going to talk about online selectors. So S, which goes from K star to X. Okay, so by K star, I mean just the string with alphabet K. Okay, so a sequence, just a sequence of sets in my family of sets. So this is an online selector. And this is really the focus of this course. If for any t in n, and any sequence k1 up to, or let's say I start at 0, k0 up to kt in k, we have the following property. S on the sequence k0 up to kt, this is an element of kt. Okay, so now the selector can use memory. Okay, an online selector has memory now. This is a big difference. Now, notice that, note, it becomes trivial to satisfy the classical Lipschitz if K prime is presented, let's say presented after K. Okay, so what I mean is if now, instead of the inequality that we had before, you look at the distance between S of K and S of K prime. Okay, so before, right, we were looking at the distance between S of K and S of K prime. But now we have memory. So now let's say I give you the set K, and then I give you the set K prime. Okay, so the set of K prime is given after you. And I want, just like before, you know, that this is smaller than the Hausdorff distance. Then I claim this is trivial because I can select any point in K. And then when I get K prime, I can just be greedy and move to the closest point in K prime. Okay, so for greedy, this is clearly smaller than the maximum over rho in K of the minimum over rho prime in K prime of the distance between rho and rho prime with constant 1, right? Okay, so when you have memory, this becomes trivial. The one-step inequality becomes trivial to satisfy. And you see on the right-hand side, I have this strengthening of the Hausdorff distance, where I don't need the max, you know, over this quantity and the one where K and K prime are flipped. I just look at, now there is an order. K comes and then K prime comes. But this inequality written like this, it has a very natural generalization to any sequence. Now, if I have a sequence, I can just look at the total distance my selector has moved, and I want to compare to the total distance I could have moved to satisfy all the requests from the worst starting point. So this is going to be the definition of online Lipschitz. So let's say, so this was for greedy. So now online Lipschitz is going to be the following. I want the sum, let's say for t equals 0 to capital T, of the distance between S on K0 up to KT, and let's say T minus 1, or maybe, sorry, maybe let's say 1 to T, and I want KT minus 1, and S of K0 up to KT. Okay, so this sum is the total distance that my selector has traveled to satisfy all of those requests. And I want this to be smaller than L times the worst starting point, the max over rho in K, of the best I can do from this worst starting point, of the minimum over row 1, let's say, okay, row 0 in K0, and row 1 in K1, etc., up to row t in Kt, of the sum of the distances between row t minus 1 and row t. Okay, and this is the quantity we're going to be interested in, this online Lipschitz. Okay, so again, I get this sequence of requests, and I want to say my algorithm, my strategy, my selector, online selector, it's not traveling much more than the best I could have done in hindsight, if I had been given all those requests in advance.
Sorry, and also
Yeah.
the difference with the previous setting. Before, the selector was didn't have memory.
Yeah, it didn't have memory.
It just select if you receive the same set, it gives the same output. Yeah.
Yes.
So why when you said that it's triggered, this note that you put there?
Yeah. So here you see, so this inequality is true for the greedy algorithm. So what is a greedy algorithm? On the first set, it's just select some point, any point. And now, on any new set, it just moves to the closest point. I mean, this is the most natural algorithm.
In K prime.
In K prime. Just move to the closest point in K prime. Then the value of this distance is clearly smaller than the worst starting point and the distance to the worst starting point. I mean, this is just true. And this is, one element in the house of distance. Okay, so for one set, it is trivial. But greedy fails for sequences. I mean, here, think of the following. Maybe let me use just briefly another color. Let's say I have a metric space which is 3 points, like this. A, B, and C. Okay, so A is very far from B and C are pretty close to each other. And let's say you get the following request sequence. So you first get the set B. Okay, you have to be in B. Then you get the set AC. Okay, so if you're greedy, you were in B, you move to C. Then you get the set AB. Okay, you were in C, if you're greedy, you move to B. And so on and so forth. Okay, so I keep giving you AB, AC, AB, AC, AB, AC. So if you're greedy, you keep moving. But the right thing to do is to realize that A was a common intersection point and to move to A. Okay, so this will be the whole philosophy of the course, is that you have to recognize at some point that you were making a mistake, but then those mistakes, you didn't do them for nothing. You have learned something about the problem, and then you just move to A, and then you're good. Okay, so I'm going to explain this in the second lecture. But this shows to you that greedy is certainly not online Lipschitz. Okay, and I would say that this inequality, we have at the moment a very weak understanding of this inequality, of what it means.
So, in some sense, when you're taking the maximum over row 0 in K0,
yeah,
you're kind of assuming that you're giving row 0 as an adversary. Like,
yes.
I would think that maybe if you allow randomization in first step, maybe you can avoid like such a worst case as an algorithm, right?
Yes. Yeah, so maybe let me make a comment on this, which is so this type of problem has a long history in theoretical computer science. Namely, this is a competitive analysis. Okay, so what is competitive analysis? And this will go to your question. So so an algorithm, so we also say that, so we are L competitive, so the definition of L competitive is going to be same inequality with, let's say, plus C on the right-hand side, and some arbitrary row 0 for opt. Okay, so I'm saying a lot of things here. So I will refer to this quantity as opt, and I will be a little bit careless and sometimes refer to the quantity as opt and sometimes to the sequence of points selected as opt. Okay, so I will use this terminology. Now, classically in online algorithm, you say that the opt, it starts somewhere. It's in some state. Maybe it's the same as yours, maybe it's not. Okay. And you want to satisfy this type of inequality, but you allow yourself a little slack. You allow some additive constant. And the only requirement is that this constant is independent of the request sequence of K1 up to KT. Okay, this is some universal constant. All right, so this is a classical definition, and we're going to work also with this definition. So sometimes I will talk about being L online Lipschitz, and sometimes I will talk about being L competitive. And these are morely the same thing. It's just in L competitive, I allow myself some extra slack, some little constant, additive constant. I mean, not necessarily little. It could be a big constant. Okay, thanks. It could be a big constant, but the point is that this quantity, the way you think about it, is that this quantity is growing. So maybe it's going to be very big. Okay, good. So let's see. Let me see what I want to do next because I'm running late. Yeah. So I will do that. Okay. So okay. So if maybe I give you an example of online Lipschitz, of what it means to be online Lipschitz, and I will defer some of the applications to this afternoon. Okay, hopefully you see that this is abstract enough and general enough that it covers many interesting problems. I realize maybe it's a bit dry because it's so abstract, but this afternoon we're going to talk about a cost function version where you have cost and you have to make decisions based on those costs. So maybe it will be a little bit more concrete, but I will defer that to this afternoon. Okay, assuming that this is motivating enough. So what I'm going to talk about now, just to give you a feel, is how to be online Lipschitz. We just saw that greedy is not online Lipschitz in the simplest scenario, which is the uniform space. And already that space has a lot of application, which we're going to talk about. Okay. So uniform space, by that I mean X is finite, and the distance is just trivially 1. Okay, so the distance between any two states is 1. Okay, it's kind of a trivial distance. So here is a theorem. There exists n online Lipschitz selector. And this is the best one can do. Okay, so let's prove that. So I'm going to prove this now, and then I will show to you again, I feel like I keep saying that, but one of the key points of the course, which is going to be that you can get an exponential improvement by allowing randomization. Okay, so this is going to be the next theorem, but let me just prove this one first. Okay, I will do the proof upstairs. Okay, so is the statement of the theorem clear? Does it make sense? So let me do the proof up there. Okay, so I will give you an algorithm, a strategy. The strategy is going to be a marking strategy. So it's called the marking strategy. And it goes like that. Upon receiving KT, the request KT, mark all unfeasible, non-feasible states. Okay, that is x minus kt. Okay, so I'm in this space, okay, which is uniform. So all the points, they are distance 1 of each other, and I'm given some set. This is a feasible set, and what I'm going to do is that I'm going to put a mark on all the sets which are not all the elements which are not feasible. And the intuition, the key point that you should have in mind is that these are places where if opt is not paying, it cannot be there. If opt was in one of those marked places, then he would have had to move. He would have had to pay. Because the whole difficulty of this online Lipschitz is how do you measure this? How do you measure this quantity? How do you talk about opt? Opt, maybe I should make this point very clear. Opt sees into the future. Right? Opt sees all the sequence. He's making decisions which are incomprehensible to us because he's making decisions based on the future. So it's very hard for the algorithm to think about that. Okay, and this is the whole difficulty of online algorithms and online Lipschitzness, is that the algorithm it has to make decisions based on what it sees currently. But he's competing with someone who sees everything, who sees all the future. Okay? And this is one way around this. So of course there is a loss for this, and here we are saying the loss is at most n. And the reason is this marking strategy. So again, all the unfeasible states, I know that if opt was there, he paid 1. He moved. Okay, so let's mark them as places where opt cannot be, and if it was there, then anyway it paid 1. Okay, so we mark them. And then, so this is just a marking, but now, how do you move? So when, yeah. Great, thanks, because this one is indeed dying. So when, great. So when you have to move, just rho t minus 1 is not in kt. Okay, so let's say right now you get a set of feasible states, and the state in which you're currently sitting is not feasible, you have to move. Then you just move to an unmarked location. When you have to move to an arbitrary, unmarked location. You have to move to an arbitrary location. That's the algorithm. That's the strategy. Now here is the point. Here is the analysis. So define a block to be a sequence from, let's say, first mark. Oh, and I forgot, a key point is that if all marked, then unmark everything. Okay, so once you have marked all the location, then you know no matter where opt was sitting, it must have paid 1. So then you just unmark everything. Okay, so let's say define a block to be a sequence from the first mark to 0 marks.
Sorry, the marking strategy is accumulating the markings over the...
No, let's say it's just your mark or not marked. There is no counter. It's just...
No, but so far it seems that you receive KT, you mark everything that is not in KT?
Yeah, and these marks are staying.
That's what I mean.
Yeah, it's staying until everything has been marked, and once everything has been marked, you unmark everything. So a block is just a sequence from the first mark to the point where you get 0 mark. And the point is that in a block, opt pays at least 1. Because you know there is no location, I mean all the locations have been marked. So all the locations have been unfeasible at some point. So you opt had to move at some point. It had to pay 1. And what about the algorithm? Well, the algorithm, it moved at most n times because it always moves to an unmarked position. So alg moved less than n. So that's it. That's your proof of n online Lipschitz. Okay? Now let's do the proof of the lower bound. Okay, so the proof of the lower bound is very simple. It's just like this. So this comes back to one of the original questions about whether the sequence is adaptive or not to the algorithm. So if the algorithm is deterministic, then we can think that the sequence is adapted to the algorithm because it's just everything is deterministic. So here is the sequence. So kt is just going to be x minus rho t minus 1. So just wherever you're sitting, this guy becomes unfeasible. Everything else is feasible. This is a sequence. If you want, it's a sequence defined inductively. Okay? So then alg, yeah, fine, yeah. So alg pays 1. Pays 1 every step. But what about opt? Well, there is only one guy that becomes unfeasible. So, I can just move to the location which is going to become infeasible the latest in time. And this will take at least n step. Okay, so opt pays less than 1 every n steps. So I pay 1 every step, but opt pays 1 only every n steps, or maybe even more. So this gives me a lower bound of n. Okay, and now let me conclude in the last 5 minutes with the exponential improvement with randomization. So here is a theorem. There exists a O of log n randomized online Lipschitz selector. And this is best. Okay. So exponential improvement. And when I say randomized, so I'm going to use randomization. And now what I want is the online Lipschitz inequality to be true in expectation. Okay. So here is the proof. So the algorithm is move to a random unmarked location. Okay, instead of moving to some arbitrary unmarked location, I just move to a random unmarked location. And the point is that the adversary, if you think about the sequence as an adversary, the adversary doesn't know where I moved. Okay, the sequence is fixed beforehand and I'm randomizing. So the adversary doesn't know where I moved. So the next location that he's gonna exclude is gonna exclude me only with probability 1 over n at the beginning. Then with probability 1 over n minus 1, and so on and so forth. So the analysis goes like this. is let fi to be the expected number of moves when there are, let's say, I unmarked locations. Okay, so all the locations have been marked except I of them. So now I can think about what is going to be the next location which is marked. The next location which is going to be marked, it's going to be the location where I sit with probability 1 over I. Okay. So what we get is that fi, the number of moves, is equal to 1 over I. That's, if I get hit at the location, the random location where I moved. And then after that, there are I minus 1 unmarked locations, so I get plus fi minus 1. Okay, and when there are only one, f1 is 1, so this implies that fn is just the sum for I equals 1 to n of 1 over I, which is roughly log n. Okay, so you get this exponential improvement just by randomization. Okay, and the lower bound, I will leave it as an exercise. It's based on a coupon collector argument. So maybe I can just say it orally. So the proof is like this. So you remember the coupon collector is, I have this n location. Let's say I hit, instead of hitting, here I was hitting a fixed location. Let's say I make a random location unfeasible. How much time do I need to wait so that I have picked all the locations? This is a coupon collector argument. What you get is n log n. Okay, so if kt is, say, x minus some rho star t, where rho star t is random, then we need of order n log n steps to hit all locations. Okay, this is a classical coupon collector argument. Now, that means that in those n log n steps, opt has paid only 1. Okay, because it could have moved to this very last location, the one that needed n log n step. So opt paid only 1 in n log n step. What about us? Well, us, we get hit with probability 1 over n every time. Okay, so in this n log n step, we have been hit log n times. So the algorithm has been hit log n times, and opt has been hit only once. So this gives you the log n lower bound. Okay, so the exercise is to think again about this proof and make sure you understand it. Okay, and I think we should break right for the coffee.
Yes.
Okay.
So let's thank Sebastian.
Yeah, thanks.